So that involves multiplying the x component of A and the x component of V and the y component of A times the y component of V. So let's see. I get minus 7.22. All right, so now we know what the cosine of theta is, because the cosine of theta, I'm going to need more room, I'll write down here. Cosine of theta is A dot V over A times V, and that is minus 0.957. Okay, so that means theta is equal to about 163 degrees. Okay, so we can determine the perpendicular and parallel components by just doing this. So A parallel is just the magnitude of A times the cosine of theta. And I get minus 0.71, let's call it. Okay, what does the minus sign signify? It signifies that the parallel component of A is actually in the opposite direction of the motion. So at t equals 2 seconds, we're up here somewhere, and the parallel component of A must be acting like that. Look at that arrow. That looks about right, doesn't it? Now let's find what the perpendicular component of A is, the component that tends to turn it. That's going to be A times the sine of theta. And that's 0.22. This is in meters per second squared. And this is in meters per second squared. Okay, so those are the two components, perpendicular and parallel. Anybody have any questions on how this works?
Yeah, I have a question.
Go ahead.
Is it safe to assume that A parallel will always be equal to A cosine theta? And same with the...
That is always correct. A parallel is always A cosine theta.
Okay.
And A perpendicular will always be A sine theta. Theta will always be between 0 and 180 degrees, so the sine of theta is always going to be positive. But the cosine of theta could be negative or positive. All right, good. Okay, let's talk about the most interesting case, which is going to be projectile motion. let's look at the situation. Simplest case is going to be a horizontal surface. I launch a projectile with a speed v0 at an angle theta. And its motion is going to look something like that. Now that motion is always going to occur in a plane because the vector v0 and the vector for gravity, g, which is in the y direction, minus y direction, those two vectors form a plane. So this motion will always occur in the plane, and I'm going to simply call this plane the XY plane, and I'm going to let x0 equal y0 equals 0. In other words, I'm launching from the origin. I don't have to, and I will generalize this later. But let's say for now that we're launching from the origin in the XY plane with an angle theta with respect to the x direction, which is the horizontal direction. Okay, so what are our kinematic equations? Well, the initial velocity, v0x, is v0 times cosine theta. And the initial velocity in the y direction is v0 times the sine of theta. So our kinematic equations become v in the x direction is simply equal to v0x. Oh, and that's it. Because there's no acceleration acting in the x direction. The acceleration acts only in the y direction. So I'm going to write down acceleration is equal to minus g. And if I want to make it a vector, we'll do that. Okay. Now we'll work out x as a function of t. Well, that's going to equal x0 plus v0x times t, but I've already said that x0 is 0. Okay, what about the y direction? Well, v sub y is going to equal v sub 0y minus gt. And the y position is going to equal y0 plus v0 yt minus 1/2 gt squared. And of course, y0 I have set to 0. So these are my kinematic equations. V in the x direction is equal to v0 cosine theta. X is equal to v0 cosine theta, cosine theta times t. Vy is equal to v0 sine theta minus gt, and y is equal to v0 sine theta t minus 1/2 gt squared. All right, those are my 4 kinematic equations that govern this motion, and I can rearrange them any way I want. But let's use them the way they are. So let's see, what can I learn about this motion? Well, one thing I can learn, and I'm going to need more room here, so I'm going to erase all this. One thing I can learn is that right here at the apex of the motion, what can I say about the y component of velocity?
It's 0.
The y component of velocity is 0 because I have an x component of velocity, but no y component. So that means dy is 0, but that must equal v0 sine theta minus gt. So what is the time to get to that point? The time to get to that point, t, is equal to v0 sine theta divided by g. Now this motion is completely symmetrical in the absence of air friction. So in the absence of air friction, the time it takes to go from here to here and the time it takes to go from here to here are the same. That means the total time of flight, I'll just call this T1. The total time of flight is equal to 2 v0 sine theta divided by g. Okay, now what else can we learn from this? Well, what is the maximum height here, h? What's the height at the apex? Well, I know the time that it takes to get to here, so I can plug that into this equation. Y at this point is equal to h. That's equal to v0 sine theta times t, but t is v0 sine theta over g. So that's the height. Oh, I'm sorry, I lost a term, didn't I? I forgot this term. Oh, Dummkopf. Okay, minus 1/2 g times t squared, which is going to be v0 squared sine squared theta over g squared. So those cancel. And the height is v0 squared sine squared theta over 2g. Okay, that's the height. All right, that's good to know. Gee, what else can we know? What about the range? This value right here is the range, isn't it? So how would I go about determining the range? Well, I could put in the time of flight here, and then x will be the range. So the range r is equal to v0 cosine theta times the time of flight, which is 2 v0 sine theta over g. And there is a useful trigonometric identity which tells me that 2 sine theta cosine theta is equal to the sine of 2 theta. So I can write this as v0 squared sine of 2 theta over g. All right. What else can I squeeze out of this? Well, what is the angle theta at which the range is a maximum? So here's the equation for the range right here. What value of theta maximizes this function? What do you think, Joshua? Well, what's the maximum possible value of the sine function?
Is it 0?
You mean theta equals 0? Well, 2 times 0 is 0, and the sine of 0 is 0. Andreas, what's the maximum value of the sine function? What's the greatest value the sine function can have?
1.
1. And at what value does that value occur? At what angle does that value occur?
90 degrees.
So I need 2 times theta to be 90 degrees.
So 45
So what's theta
degrees.
max?
45 degrees.
There we go. And you kind of know that intuitively. When you were a kid with a BB gun and you wanted to see how far you could shoot your BB, you'd shoot it at an angle of about 45 degrees. Of course, air friction affects it, but it would be about 45 degrees. All right, that's good. Okay. Now, there's another thing that I'm going to derive from this that is extremely useful. And, oh, and what is, so theta max is 45 degrees, but what is R max? R max is actually V naught squared over G, isn't it? So that means I can rewrite R, if I like, as R max times the sine of 2 theta. Okay, now there's an extremely useful relation here that we can derive, which is the equation of the path. Now, right now, I have the path parameterized with respect to the time t, because I have x as a function of time, and I have y as a function of time. I'd like to eliminate the time between them, and then I will end up with an equation relating y and x. And I'm going to write my equation of the path as y as a function of x. That is an extremely useful relation. In fact, looking at your problems for chapter 3, most of them involve some clever use of the equation of the path, although you can do things in more than one way. So let's figure out what the equation of the path is. So I know that x is equal to V0 cosine theta times t. So I'm going to solve this for t. T is equal to x divided by V0 cosine theta. Now I know that y is equal to V0 sine theta t minus 1/2 g t squared. So all I have to do is substitute in for t. And now I have an equation between y and x. So let's do that. Y as a function of x is going to equal V0 sine theta times t. Well, t is x divided by V0 cosine theta. So we'll simplify that, but let's go on to the next term. Minus 1/2 g t squared, which is x squared over V0 squared cosine squared theta. Okay, so let's simplify this. Y of x is equal to x times the tangent of theta minus gx squared over 2 V0 squared cosine squared theta. That's the equation of the path, but I've made an assumption here in order to keep the algebra simple. And my assumption is that the motion begins at x0, y0 equals 0. So I have to move in order to use this particular equation of the path, I have to move my origin to where the projectile motion starts. So let's do an example. Let's say that I have a cliff, and let's say this cliff is 100 meters. And let's say there's 100 meters is actually really large. Let's not do that. Let's try to make it more realistic. Let's just say 20 meters. And then at the bottom of the cliff, there is a bunch of rocks. And then water. So let's say a person wants to run along the cliff and jump off the cliff, and he doesn't want to hit the rocks. He wants to hit the water. He has an initial speed V0, and this distance here, let's say, is 5 meters. So this h is equal to 20 meters, and this x is equal to 5 meters. Okay, what is the V0 that he has to jump off the cliff with in order to hit the water instead of the rocks? Well, the equation of the path is y of x is x tan theta plus g x squared over 2 V0 squared cosine squared theta. But that's not correct, is it? What did I do wrong? Yeah, forgot the negative sign. So I have to put a negative sign here. All right. Now that presupposes that my x equals 0, y equals 0 is right there. V0 is in the positive x direction. So what does the angle theta equal? The angle theta equals 0, doesn't it? So if that's the angle theta is equal to 0. So what is the tangent of 0? The tangent of 0 is 0. We want to hit this point right here to find the minimum value of V0. So that means y equals minus h that must equal minus g times x squared, and x is 5 meters, divided by 2v0 squared, and the cosine of 0 is 1, so cosine squared of 0 is just 1. So I can solve this for v naught squared, and I get, or for v naught, and I get v naught equals g over 2h square root times x, where x is 5 meters and h is 20. Okay, does everyone see how to use the equation of the path to solve this problem? Now you could use the kinematic equations directly, the time parameter equations directly, but then you have to figure out the times. You'd have to figure out how long does it take to fall, and then what speed does he have to go at in order to go at least 5 meters in that time. It's much easier to use the equation of the path.
I do have a question.
Go ahead.
Where did cosine squared theta go?
Well, theta is equal to 0. What's the cosine of 0?
Oh yeah, 1.
Okay.
And then same thing with tan theta, right?
Tan theta is equal to 0 because theta is equal to 0.
Thank you.
Can I ask you a question that's just more out of curiosity? And I
Yeah.
don't know if you know the answer. It's not quite related. How it's like in this exact scenario, like I don't know who's been clipped or jumping off the rocks, but like sometimes like you have to look at it and your brain like does it. Like how do you know how we do that? I know that's not really physics.
Oh, how does your little internal brain computer figure out how fast you have to go in order to do it?
Is that like rough math or is it experience?
It's got to be experience. Do you trap shoot? Do you ever shoot trap?
No.
Well, there's a
I
whole
understand the
theory.
principle.
There's a whole theory called the Churchill method, where if a target goes flying out there like this, there's a target flying out there like this, and you're standing here with a gun. You start the gun behind the target and swing it through, and your brain will automatically pull the trigger at the right instant. And the speed with which you swing it, after a little bit of practice, your brain will know. It's sometimes called instinctive shooting, or also the Churchill method, but it really works. I mean, the first time I ever shot trap, I couldn't hit anything, and a guy launched a target without telling me and said, "Oh my God, there's a target, shoot it, quick." And I instinctively did exactly this and broke the target. And then I understood. So yeah, your brain can certainly do it. I don't know how. You have to have at least some data in order for your brain to have an idea. You have to have some experience.
I was just curious because like that's always really interesting to me, or like reflexes and stuff like that.
Oh yeah, it's amazing what your mind will allow you to do if you leave your mind alone and stop trying to think through everything. It's quite amazing. In sports, I don't know what sport you play, but let's say basketball. I mean, do you think through everything you do? Or do you instinctively know how hard to throw the ball to make it get to the basket? Or what to do to dribble around your opponent, or whatever? Yeah, give yourself a little experience and your mind will take over, and you don't have to consciously think about it. It's amazing. It really is. Okay. Oh, I've got a whole bunch of interesting problems here. Well, you know what? Let's ask ourselves this question. Let's say that we're on a battleship. Here's the ocean. And Here's the gun on my battleship. And here's my target. So given a certain V0 and a certain angle theta, I can hit that target. But there are actually two, for a given V0, assuming that the target is within range for that V0, there are actually two angles theta at which you can hit the target. The first one is low angle, and the second one, oops. Okay, okay, screen sharing, there we go. Sorry about that. Can't really draw because all that stuff is in the way, but that's the other solution. So what are these two angles theta? Well, one of them, theta, since the range is R max times the sine of 2 theta, one of these is 1/2 the arc sine of R over R max. That's the sine minus 1, the arc sine. Okay? Call that theta 1. The other angle, theta 2, is 90 degrees minus theta 1. So if given your V0 for your gun, if you can hit the target at an angle of 20 degrees, another angle for the same V0 that will hit the target will be 80. What happens if your target is already at maximum range? Then the angle that you have to fire at is 45 degrees. And 90 minus 45 is 45. So there's only one angle that works when you're at maximum range. And of course, no angles work if you're beyond maximum range. Okay, so those are the two angles at which you can hit a target. If you were a battleship, which of these two would you rather use?
The lower one.
Ooh, no, the higher one.
Why is
Because
that?
you want your projectile to go through the decks and explode in the bowels of the ship and possibly go all the way through.
But wouldn't it also have more time traveled? So you have less accuracy.
Oh, I don't think there's a matter of less accuracy. The time of travel is certainly longer.
Oh, that
But
target's not moving; it's stationary.
I don't think that matters. Well, the moving target is included in part of the range finding. Oh, that's all included. The gun is computer controlled so that it only fires when the deck is exactly level. Because of course the thing's moving in the water, right? So it's bobbing a little bit in the water. Yeah, no, this is the preferred. Plunging fire is preferred.
This is actually physics. So that wouldn't be two separate equations. Because if something takes longer, then it wouldn't be the same equation, correct?
It's not the same path. Yeah, the equations aren't the same because theta is different.
It's my question is the time of fire of those two equations shouldn't be the same.
No, the time of flight is not the same.
Okay. No,
yeah, the time of flight is not the same.
The time of firing.
You mean the time it takes to go from here to here?
No, the initial onset of the charge should not be the same then, correct?
The V0 is the same, only theta is different.
My thinking is if something's moving at let's just say it's moving at 10 miles an hour, and then you're going to fire this projectile, and then one takes longer than the other, they can't hit the same point at the same time if one takes
Oh, that's completely different. That's completely different. Yes. The time of flight T1 for this is different from the time of flight T2 for this. Absolutely. No, I don't mean that they hit at the same time. I meant which of these two paths would you choose to fire a single projectile from your battleship.
Okay. I guess my, like, it's point A and point B. Point B is point of impact. Point
Yeah,
A, like,
This point
you
is the
wouldn't
same, and this
release from
point is
point
the
A at
same.
the
There's
same
two different
time.
paths that connect them.
Okay. I just don't know how to ask my question, but I get it.
Now, modern field artillery does what you suggest. Modern field artillery, the new 105 millimeter gun, uses liquid propellants, so it's a howitzer. So it uses liquid propellants, and it is computer controlled in terms of changing theta and V naught. So theta changes and V naught changes, so that the gun will rapid fire within less than a second, 3 shells, and those shells land at exactly the same place at exactly the same time. So they're designed to do that. Obviously, 3 of them hitting the point is more effective than 1. Okay. Let's look at artillery on a cliff. So here's my cliff. And I fire from this position right here with an initial velocity and an angle theta with respect to the horizontal. And we'll call this x equals 0, and we'll call this x equals r, the range. All right. So let's determine what the range is. There's more than one way to approach this problem. Let's do it this way. The range r is equal to V0 cosine theta times the time of flight. And we'll let y0 here equal h. So this cliff height is h, and this is x equals 0 and y equals 0 down here. So notice I'm not using the equation of the path that I had last time, but I could. So that's r. Then 0 is equal to h. So y, when y equals 0, I'm here or I'm here, plus V0 sine theta times the time of flight minus 1/2 g times the time of flight squared. So the time of flight is the time it takes to go from here to here. Now what I'm going to do is eliminate these two, TF from between these two, and I will get r squared minus 2v0 squared sine theta cosine theta times r divided by g minus 2h v0 squared cosine squared theta over g equals 0. So I have two solutions for r. R equals, from the quadratic formula, V0 squared cosine theta sine theta over G plus and minus the square root of V0 cosine theta. I forgot to put that on front. And this is V0 squared sine squared theta divided by G squared plus 2H over G. Okay, so now we have two solutions for R for this problem. The solution with the positive sign here corresponds to this distance right here, from here to here. Now, what does the negative sign solution represent? Anybody have any ideas? Well, it represents another value of X, which I've renamed R, another value of R where Y is equal to 0. And that corresponds to this value. Right here. This from here to here is the other value of R. So on the path of this projectile, there are two solutions for Y equals 0. I fire it from the cliff here. I can also fire from the ground so that my projectile goes through this point right here at this angle with this V naught. And that's going to end up here because it's on the same path. So that's what the two values of R represent. One of them is the distance behind the cliff that you fire from the ground in order to go on the same path. And the other represents the range you get if you fire here from the top of the cliff. Okay, is everybody sort of getting a handle on this? All of these projectile motion problems are nothing but manipulating the equations for X, Y, V sub X, and V sub Y as functions of time. That's all they are. All right, I'm going to give you a problem to think about. So I'm going to assume an angled cliff face. And I'll assume this cliff is so high and this face is at a constant angle that if I launch a projectile with a V0, that it will hit somewhere on the cliff face. And the question is, where on the cliff face do I want it, will it hit? Given a speed V0, and I'm assuming it's horizontal here, and this cliff face is at an angle theta. That angle right there is theta, or if you prefer, this angle is theta, either way. Now there's more than one way to solve this problem, but many times in this class, we're going to take our coordinate system and we're going to rotate the coordinate system to be a more convenient set of coordinates. So for example, I am going to define a new coordinate system that aligns with the cliff face. And I'm going to call this the new x coordinate and this the new y coordinate. Now, my gravity vector is like this. G is pointing this way. Because here is the trick. Now, I'm basically solving a problem in which I'm launching at an angle theta. Where is it? There we go. I'm launching at an angle theta on a horizontal plane because I've rotated my coordinates to make it more simple. But there's a price I pay. And the price I pay is the acceleration due to gravity in the x direction is no longer 0. That means that my kinematic equations now have to contain an acceleration term in the x direction as well as the y. Here, our acceleration is only in the y. Here, we're assuming an acceleration in the x direction and the y direction. So that's theta. This angle is 90 minus theta. So the acceleration in the x direction is going to be g times the cosine of 90 minus theta, which is the same as the sine of theta. But I have to have a negative sign because the component of g is along, oh, I'm sorry, that is the positive x-axis. So I need a positive sign here. Okay. So a sub x is g sine theta. Now, what about a sub y? Well, you might guess a sub y has got to be g cosine theta, but it's minus g cosine theta. So the component in the y direction here, if that's theta, that's 90 minus theta. This is theta. It's g cosine theta, but it's along the minus y-axis, so I have a minus sign there. Now my kinematic equations are a little different, but I can still manipulate them in exactly the same way. So my v sub x is equal to v0 cosine theta, right? Plus g sine theta t. And my x position is v0 cosine theta t plus 1/2 g sine theta t squared. And my velocity in the y direction is equal to v0 sine theta minus g cosine theta t. And my y coordinate as a function of time is v0 sine theta t minus 1/2 g cosine theta t squared. Now, use those equations in whatever way you like, and there's more than one way to do it, in order to determine where is that position on my new x coordinate where the projectile hits the cliff face. And I'm assuming the cliff face is sufficiently high that it will hit the cliff face instead of the, instead of the horizontal plane below the cliff. Okay. So, you want to think about that problem? And I'll see you again on Wednesday. Does anybody have any questions or anything they want to say?
Professor, I just had a quick question. Do you have a class after this?
No, I do not.
Can I ask you a couple quick questions after? It's like, they're not all class related.
That'll be fine. Sure. So you just, after everyone else has left the meeting, you stick around.
All right, no problem.
Okay. Does anybody else have anything, any questions or anything else they want to say? Did you have something, Michelle?
No, I was just gonna say thank you and have a good